involve looking at one and the same process from two different inertial reference frames, from the point of view of two different observers, in other words. We'll call these observers for today S, which, depending on how the story is going, that's the ground frame. Or maybe we call it the rest frame, or the lab frame, something like that. And then another reference frame, which I'll call S prime. That's the train frame. An observer riding along on the train. Or maybe we call it a moving frame. All the rest and moving is a little bit bad language because, of course, from the other point of view, it's he who's at rest and the other one is moving. Or maybe in some contexts this would be the rocket frame. We're talking about the twin paradox and somebody flying off at high speed in a rocket. Anyhow, all of the arguments that we've dealt with involve two different inertial reference frames, one of which we'll call S, and the other which we'll call S prime. And then comparing what the observers in those two frames observed, we come up with with all of the phenomena of relativity. So far, we've been getting back and forth between S and S prime in a purely ad hoc way, usually via one of those quaint little parables or Duncan experiments of Einstein's, and thereby deducing time dilation or contraction or whatever it was. Today I want to show you a systematic, foolproof way of getting back and forth between S and S prime. If a certain physical process is described a certain way in S, how is it going to be described in S prime? Not ad hoc for each particular case, but systematically for all cases. If you stop to think about it, every physical process consists of a sequence of events. The word event in relativity is a technical term. An event is something that occurs at a particular place at a particular time. Thus, for example, an explosion of a firecracker, that's an event. But your camping trip in Alaska, it's not an event because it occurred over a period of time in a variety of different locations. An event is something that occurs at a particular time and a particular location. Got it? It's a technical word in this business. We label an event, identify an event, by giving the coordinates of the position where it took place and the time that it occurred. The coordinates in Cartesian system, x, y, z, that's where it occurred. And the time, t. So to specify an event, you need to list four numbers, x, y, z, and t. What I would like is a dictionary from going from the S to the S prime coordinates. In other words, if observer S assigns to a particular event the coordinates x, y, z, t, question, what coordinates x prime, y prime, z prime, t prime would S prime assign to exactly the same event? Got a question? I use coordinates in the general sense of all four of them, x, y, z, and t. So suppose that S assigns coordinates x, y, z, and t to some event. Question. What coordinates x prime, y prime, z prime, t prime does S prime assign to the same event? What coordinates? That's the whole issue. What we're looking for is a dictionary, if you please. A dictionary that translates from the language of S over to the language of S prime. A dictionary in the sense of a foreign language dictionary, where you're translating a description in French into a description in German, or back and forth. This is translating a description in the language of S into a description of the same thing in the language of S prime. Got the picture? So we need a dictionary. And that dictionary is precisely the Lorentz transformation. But before I do the Lorentz transformations, I want to back up and answer the same question classically. How would Galileo, or indeed anybody before Einstein, before 1905, have answered this same question? They would have considered it a pretty trivial, stupid question at that point, but it will set the scene at least. We call the pre-relativity answer the Galilean transformations as opposed to the Lorentz transformations, which will be the relativistic answer. So, let's see. I imagine that I've got two systems, S and S prime, and for the sake of simplicity, let's assume that S prime is moving along the x-axis of S. So here's S, X, Y, I won't put in Z. This is the reference frame S, the rest frame, or the lab frame, whatever you're calling it. And here, maybe I'll make it yellow, is the S prime frame. It has coordinates x prime. By the way, I might as well orient S prime's axes so the x and x prime axes are along the same direction, and the y and y prime axes are in the same direction, and same for z. So this is y prime, x prime. This is S prime. And S prime is moving along to the right at speed v. You know, you could make life really miserable for yourself if you have the S prime reference frame moving off at some oblique angle or something like that. It would tangle you up in nasty arithmetic, but it doesn't change anything in principle because, after all we got one reference system that's here, one reference system that's moving. Let's stick the x-axes along the relative motion, okay? We're not losing any generality, no loss of generality in principle there. It just makes life a little easier if we say the relative motion is right along the common x prime axis. But S prime is moving along at speed v in the positive x direction. So, say that S prime moves in the x direction at speed v. Now I need to tell you how we're going to coordinate the clocks. We'll do this in the natural way. Set the master clocks. In each system, there's a master clock that's sitting there right at the origin. I will set those to t equals 0. Also t prime is equal to 0 at the moment that the origin of s prime crosses the origin of s. Fair enough? I'm setting this up altogether more carefully than one would ever bother with if you were really talking about pre-relativity physics, but I'm anticipating being very careful for the relativistic case. So we set the master clocks at the respective origins to t prime equals 0 at the instant the origin of s prime passes the origin of s. In other words, when x equals x prime equals 0, the two origins coincide, at that moment we will agree. Set your clock to t equals 0, set your clock to t prime equals 0. And then we'll let them run from then on. Got the picture? So that's just establishing the rules of the game, convenient rules of the game. Now, what was the question again? We imagine that some event takes place. Event will be green, probably not too good on a green blackboard. How about pink? Event is pink. Here it is. Firecracker explodes. That happens at time t, which I've drawn here with the yellow where the s prime coordinate system has moved over a distance v times t. Isn't that right? Because I set the clocks to t equals 0 when the origins coincided. It's now been moving for a time t, and at that time this explosion takes place. The coordinate x is this distance here, and the coordinate x prime is yellow, this distance here. Got the picture? This is, as I say, stupidly simple. Nobody would ever have dreamed of going through this argument before Einstein, but now we have to be much more careful. So what's the connection between x and x prime? The formula for x prime, the coordinate associated with that event according to the prime moving observer is just equal to x, the total distance, minus vt, the distance that his origin has moved over. So it'd just be x minus v times t. Fair enough? How about y prime and z prime? If it didn't exactly occur on the x-axis, but somewhere up here, y prime equals y, and z prime equals z. Those are not affected by the motion. And finally, the time that the moving observer would assign to this is the same as the time the stationary observer would, because in classical physics, time is, as Newton said, universal, absolute, the same for everybody. As long as we start the clocks the same, the time of this event is going to be the same in the two coordinate systems. So these are the Galilean transformations, the pre-relativistic answer to the question, how do you translate the coordinates in S over to the coordinates of that same event in S prime. Now, let's do it relativistically. How would Einstein translate the coordinates in S over to the coordinates in S prime? Point of 3, I guess, of the Lorentz transformation. Now, you might say, starting with this one here, the transformation rule for x, how do I get x prime from x and t? Well, how could that possibly be any different? It's exactly the same diagram pertains. Well, there is one very subtle difference now. I was looking at this entirely from the point of view of s. This distance here that I called on my diagram x prime is actually the length of that line according to s. But that has been Lorentz contracted in relativity now. That's been Lorentz contracted compared to what the observer s prime would say that length is. In fact, the observer in s prime would say that that length is longer by a factor of gamma than the x prime we calculated here because it has been Lorentz contracted. Because it's a moving meter stick, if you like. So what we call x prime from the point of view of s has actually been Lorentz contracted. The true, if you will, length in s prime is longer. The contracted length by a factor of gamma. That's the only difference. So x prime, according to relativity, x prime should not have been x minus dt, but simply gamma times that. That's the relativistically correct generalization of this. The only slight twist is that the x prime in this diagram was from the point of view of s, and that's not what I want if I'm talking about the coordinates in s prime. It's been Lorentz contracted, so un-Lorentz contracted by multiplying by a factor of gamma, and you get the length that s prime would assign to that same distance. So that's the transformation rule for x, for going from x and t to x prime. Just throws in a factor of gamma in what Galileo would have written down because of Lorentz contraction. Now a much more subtle question. Well, let's do the easy question first. How about y and z? What happens to them in relativity now? Nothing at all. There is no Lorentz contraction in direction perpendicular to the motion, so it's still the case y prime equals y and z prime equals z. No contraction perpendicular to the motion. So those are easy. Time, however, is not easy. How come? Well, in relativity, we know there's time dilation, there's failure of synchronization of moving clocks due to the relativity of simultaneity. Something fishy is going to happen with time. It's no longer the case that t prime is just equal to t. Question, what is the transformation law for getting t prime? This is not a completely easy question. I think that the x prime transformation is pretty easy and straightforward here. There are about 6 different ways I know of getting the transformation law for t prime. I'm going to show you the easiest way, what I think is the cleanest way to get t prime, but it sounds a little bit indirect. So in the books you'll find, each book will have its own special way of finding the transformation law for t. But this is the way that I like best. I ask you the following question. If s prime is moving at velocity v to the right relative to s, then I say s is moving to the left with the same speed v relative to s prime. Make sense? Are you dead sure it's the same velocity, same speed v? Well, actually think about it. How could it be any different? Suppose that there was some law that says if S prime is moving to the right with speed v, then S is moving to the left with speed 10 v, or something like that. Suppose that was the rule. Well, what distinguishes S from S prime? Left and right, that can't possibly mean that there's a factor of 10 in one direction and no factor of 10 in the other direction. That would be cockeyed. It's got to be the same factor either way. In fact, I think that's built into the principle of relativity itself, the first postulate of relativity, that if S says S prime is moving to the right at speed v, then S prime says S is moving to the left at speed v. If that's the case, suppose that I wanted the reverse transformation for the x primes now. Suppose that I wanted to go from x prime and t prime back to x. It would have to be exactly this same formula with one small twist. What would the twist be? Can you spot it? Of course, I would be putting primes on these two and taking the prime off that one to do the reverse dictionary. Now we've gone from German back to French. But what else would be different about that law? No, actually, I would, maybe Socratic method fails there. I would simply change the sign of v, because if going from S to S prime is v to the right, going from S prime to S is v going to the left, what did I change there? I simply flipped the sign of v. By the way, did I touch gamma? You might say, gamma, that's got a v in it. Yeah, but it's squared, right? It's 1 over root 1 minus v squared over c squared. So for gamma, it doesn't matter whether you're going to the right or to the left. It's going to come out in the squaring. So, the reverse transformation has to be the same, except that v goes into minus v. Because if S is going to the right at speed v, then S prime is going, if S prime is going to the right at speed v, then S is going to the left at speed v. Just switch the sign of v. That's a handy thing to remember, by the way, because people always list the Lorentz transformations in one direction. And occasionally you think, well, some problem comes up, you need to put the dictionary in the other direction. It's trivial. Just flip the sign of all of these, and you've got it. So here's the transformation in the reverse direction. Gamma, no change in gamma, x prime now, plus v times t prime. That's the reverse Lorentz transformation, going from prime coordinates back to unprime. Well, what I'm going to do is use this and this to solve for t prime. Very clever. So x prime, I know from there what it is. X is equal to gamma times x prime is itself gamma times x minus bt, and then plus the t prime. You see how I did that? I know that the reverse transformation is the same with the opposite sign here. Now I stuff in what x prime is gamma times x minus bt. I've got now a formula that involves x, t, and t prime. Exactly what I want. I'm going to solve for t prime. So, what do I have? X is equal to gamma squared x, that's the first term, minus gamma squared vt, that's the second term, gamma gamma v, plus gamma vt, vt prime. Now what I was solving for is t prime, so let's isolate that. Gamma vt prime is equal to, I'm going to pull all the other junk over to the other side. This is x times 1 minus gamma squared, coming from here, and then plus gamma squared vt. This term pulled over to the other side. Next step, I will divide through by gamma v. To get myself just a formula for t prime. This says that t prime is equal to, now put this term first, the v's cancel, and I have 1 gamma cancel, so this is gamma times t, and then the second term is plus 1 minus gamma squared divided by gamma v times x. What a mess. But actually, this thing can be tidied up, that expression there, 1 minus gamma squared over gamma v. Let me write it as gamma over v times 1 minus gamma squared over gamma squared. You see what I did? I multiplied top and bottom by gamma. So I had a gamma out there and a gamma squared now in the denominator. That's nice because this is gamma over v times 1 over gamma squared minus 1. Well, what is 1 over gamma squared? I lost you. I think I might have. 1 over gamma squared. 1 over would put this up in the numerator. Square it would be 1 minus v squared over c squared. So this is gamma over v times 1 minus v squared over c squared minus 1. The 1's cancel, and I get minus gamma v squared over v c squared. V cancels, and I get minus gamma v over c squared. If you got lost in the algebra, don't worry about it. You can do this at your leisure. I claim that that quantity there is nothing but minus gamma v over c squared. So let's combine these together now. I've got my formula for t prime. It's equal to gamma times t, that's the first term, minus gamma v over c squared times x. And that's the answer. This tells me t prime in terms of t and x. A little bit better way to write it, let's factor out the gamma. It's t minus v over c squared times x. If you don't like that derivation of the time transformation, look in the books and see, as I say, you can see a lot of different ways of doing it. This is a little bit of arithmetic in this part, but conceptually, I think it's the simplest way of getting your hooks into that. Let me summarize the situation here then. Conclusion. X prime, the dictionary for getting the coordinate x prime is gamma times x minus vt. The rule for getting t prime, the transformation for getting t prime, is gamma times t minus v over c squared times x. Those are the celebrated Lorentz transformations. Dictionary for translating the coordinates of an event in S over into the coordinates of that same event in T. By the way, some people would list also y prime equals y, z prime equals z as among the Lorentz transformations there. This dictionary now contains all of the information of relativity. Relativity of simultaneity, time dilation, Lorentz contraction, velocity addition, you name it. It's all contained in those equations. In fact, it's notation a little bit too powerful for its own good, because from now on, doing all things in relativity, you can simply rely on the Lorentz transformations. It's a mechanical, purely mechanical process for converting things from events from one coordinate system to another coordinate system. You never have to think anymore, which is why I was saying last time that the fact of the matter is you probably understand relativity conceptually at this point as well as you ever will, because at least if you go on in physics, the next time you study relativity, you will start with the Lorentz transformations. They'll never talk about these conceptual problems about relativity of simultaneity and stuff like that, because it's all built in. All. Relativity simultaneity. Lorentz contraction, time dilation. Velocity addition. On the owls for Friday, you get a chance to play with the Lorentz transformations and find out a little bit of their power by solving a couple of problems. Relativity of simultaneity, by the way, is clean right from here. Suppose that I had 6 events, all of which occurred at time t equals 0. So they're all simultaneous according to S. At what time did they occur according to S prime? Well, putting t equals 0, I get minus gamma v over x over c squared times x. What does that tell me? That those 6 events that were simultaneous in S are not simultaneous in S prime. Depends entirely where they're located. Some of them happened earlier than time t equals 0, the ones that are positive x. Some happen at later times. Those are the ones that are negative x. So relativity of simultaneity is built right into that equation, but all of the other effects are too. I'm going to stop here because we need to do evaluations for the course, and there were a couple of people who are going to handle this for me. So on Friday, I will talk about the Michelson-Morley experiment and Minkowski diagrams and whirl lines, a lovely way of thinking about relativity.